Hello, in this clip we're looking at the natural log function, ln, the natural log function, and we're going to be starting with the basic one, ln x, and translating it, reflecting it, and dilating it. And we'll finish in another clip, I think, with a couple of exercises. So let's have a look at ln x itself. So this is log base e, of course, and the basic variety of it looks like this one. It's the one in red, and there's a couple of noteworthy features about it. Firstly, unlike the exponential function where the asymptotes are horizontal, with logarithmic functions they are vertical, and the reason for that is that as x approaches 0, we know that the natural log, or any log for that matter, is undefined. So as x approaches 0 over here, over there, what's happening to the function is that it's becoming increasingly negative. So you can try that on your calculator. You can put in a very small value for x, maybe 0.0001, and you'll see that you'll get your function will be large and negative. So the other easy thing to identify here is the the x-intercept, and we know that that's going to happen, that this function is going to equal 0 along the function axis there when x is equal to 1. So log any base 1 is equal to 0. Okay, so they're the two essential features here, the x-intercept and the asymptote, which is not shown because it is on the function axis. Now, in this slide we're showing how to translate our basic function horizontally, and you can see the one in green here is ln x plus 1. Perhaps counterintuitively, if you start with x and you add something, you are going to shift your whole function, in this case 1 unit to the left. And of course that does check out, doesn't it? Because if we substitute x equals 0 in there, what we've got is, so x is equal to 0, our function will equal ln 0 plus 1 is 1, so that'll equal 0 as well. Similarly, looking at the other translation here, ln x minus 1, we say we move the basic 1 unit to the right, like so, and we can see that if x is equal to 2, what have we got our function equaling? Well, ln 2 take 1 is 1, and ln 1 of course is 0 again. Now do note that what we've also translated are the vertical asymptotes. So for the green one, the vertical asymptote is going to be quite clearly x equals negative 1, so we could and should draw a vertical asymptote in there, and also with the other translation, the blue one, fx equals ln x minus 1, the vertical asymptote is not drawn in, but it should be drawn in at x equals positive 1. There we go, all drawn in. Now in this view we're showing vertical translations, and a couple of noteworthy things. So as you'd expect with a vertical translation, what you're doing is you're adding, or subtracting in this case, a constant from your logarithmic equation, from your function. And once again we're going to start with the basic fx equals ln x sketch here, noting the x-intercept again and the fact that the asymptote is at x, or x equals 0, and you can compare a couple of things against that basic ln x sketch. Firstly, notice that the vertical asymptote's the same, so we're still interested in when x approaches 0, and in fact when this argument in here, what's between the brackets, equals 0. Okay, so that's not going to change if we just shift up or down, is it? So same vertical asymptote, x equals 0. A couple other things you will note is that if you compare the top one to the basic ln x function, you're simply adding 1 unit every point along the way. So whereas we've got a point here of 1, 0, for this one it is quite clearly 1, 1. So we've added 1 in the y or function direction, and similarly we subtracted 1 here, so we go from 1, 0 to 1, negative 1. And you're going to find that applies all the way along here. It might not look it down further down this way, but it is the case that you're always subtracting or adding 1 to your basic function when you're talking about a vertical translation. Now the other thing that you should plot when sketching these things is the x-intercept, and you do that in the usual way, so you let the function equal 0, and that's what I've done down here. If you look down at the bottom part of the screen here, I've let fx equal 0, so ln x plus 1 equals 0, and it's easy to solve. Ln x will equal negative 1, and converting to exponential form you get e to the negative 1 equals x, and that's not going to help you plot very much. So you get a numerical approximation and it comes out to x equals to 0.37. That's to 2dp, and I should write that in there. But anyway, I could indicate that on my axis here. You would find the x-intercept for the other function in exactly the same way, of course, and you'll discover that that's equal to 2.7183 because you're going to add 1 to both sides when you let this equal 0, and e to the power of 1 is e, and so x is going to equal roughly 2.7183, and you would indicate that there. In fact, I might do it now while I think about it. Whoops. 2.7183 is what that x-intercept is. Sorry about that slightly messy working there. Moving on to dilations now. In this little slide, what we're talking about are dilations parallel to the x-axis. Now, I'm not sure there's an easy way to remember which is which, parallel to the x-axis and parallel to the y-axis, but I mean, visually it does seem to me this is dragging these functions. You know, here's your basic one, and ln 2x and ln half x here. They've sort of been getting dragged parallel to the x-axis, aren't they? A simpler way to remember, perhaps, I mean it works for me, is that when you're talking about parallel to the x-axis, you are talking about adjusting the coefficients of x here, okay, as opposed to parallel to the y-axis, which you will see in the next slide. That's something different. Okay, so what's the go with these? Well, the first thing to note is when compared with our basic fx equals ln x function here, has your vertical asymptote changed? Well, no, of course not. And the reason is fairly straightforward, isn't it? Because we're interested in what happens. We're interested the vertical asymptote will occur where what's in brackets here is approaching 0. Okay, so the coefficient isn't changing that. In each case, it will be where x equals 0. Okay, so the vertical asymptote is not changing at all. What, of course, is changing, however, of course, is the x-intercept, and we find that in the usual way. We let our function equal 0, and you're going to discover that I think it's common sense, isn't it, that if we look at ln 2x here, what's happening is that we're basically interested when this is going to equal 1. Why? Because ln 1, well, log any base actually, 1 is always equal to 0. So we're interested in when 2x is equal to 1. Therefore, x equals a half. And if we slide down there, we could see that x is equal to a half about there. Okay, that's our basic one, of course. So, as we'd expect, the x-intercept's at 1. And here, well, we're interested in when x over 2 is equal to 1. And that's a very easy one to solve. X will equal 2 as shown there. Okay, so that's dilation parallel to the x-axis. Let's move to the y-axis now. Now the big thing here is that it say turns out that your vertical asymptote's not changing, it's still equal to, yes, the vertical asymptote is still x equals 0. Interestingly, what's happening here, your x-intercept's always the same, isn't it? Okay, and that's because what's in brackets has not changed. What's changed, of course, is the coefficient of the logarithmic function itself. But, you know, the x-intercept is always going to occur where what's in here is equal to 1, isn't it? Because ln 1 is equal to 0, and 2 times 0, or half times 0, is still 0. So that's how that works. So that's parallel to the y-axis. How do you remember that? Well, I suppose one way is that the coefficient of the log function is closer to where y would be. That's one way to remember it, I suppose. Now this slide's showing the results of reflecting our basic function fx equals ln x over here around the x and y axis, and sorry, the function axis and the x axis. So let's have a look at the right hand side here. We've got one here, fx equals negative ln x. So it stands to reason, doesn't it, that if you want to reflect this basic one in red around the x-axis, what you do is you make what's negative positive and what's positive negative, and that's the general effect of putting a negative sign in front of the ln x. Over here we can reflect our basic ln x function around the function axis by putting a negative x in brackets, so that, remember, it's got to be positive in here for our function to be defined. So if you put in negative x values, that becomes positive, and negative will become positive. And so this one here, ln negative x, is only defined when x is negative. So that's how we get that effect. And you can imagine this one here is a combination of both, reflecting it around the function axis and the function axis there, and the the negative there, and the x-axis here. So in the next clip we'll be doing some worked examples. Look out for those.